Hello, so today we are going to do this problem, which is part of Leetcode January Daily Challenge, non-decreasing subsequences. So what we have here is an array of numbers, and we want to return all the different possible non-decreasing subsequences. So basically we want to return all the possible increasing subsequence, but since they said non-decreasing, that means that equal values are allowed, but it still needs to be sorted. The order needs to be increasing, yeah. So basically, want to identify all the possible non-decreasing subsequences. So not subarrays, subsequences that have at least two elements, right? So if it's one element or empty, we don't want to count that. And we want to return the subsequences themselves in a list of subsequences. So not just the number, but those subsequences actually. And so, for example, if we take a look at this array, we could take 4, 6. We can't take only 4 or only 6, but 4, 6 is valid. 2 elements, it's increasing. 6, 7 is valid. 4, 6, 7 is valid, right? Increasing. Even 7, 7 is valid because it says non-decreasing, which means that equal values are allowed. And so we have 7, 7. We can also take 6, 7, 7, right? And that's pretty much, that's pretty much all of them. Now, how do we solve this problem? The main thing to look at are two things. One is the example, and the other one is the constraint. For the constraint, you can see here it's really small. It's 15, right? And the length can be up to 15. And if you see a constraint with the 2 digits or even less, like less than 100, then immediately know that something exponential like 2 to the power of 15 should work fine. Okay. So that should be a big hint for this problem, because 2 to the power of 15 is just 32,000 something, so it's not too big. And the other hint, the other thing to pay attention to is this is subsequences. It's not subarray. If it was subarray, we can just try every subarray combinations. So pick I from 0 to n and pick j from I plus 1 to n and try all the subarrays. But it says subsequences, which means you can skip elements. So for example, we can have 4, 7. That's a valid one. Actually, it's somewhere here. Yeah. Okay. You could also have 4, 7, 7. You can even have 6, 7. Right? Because it's a subsequence. Okay, so now knowing these two observations, let's see how we can solve it. Okay, so how would we solve this? Well, we saw that the constraint, the max is 15, the length. And so you probably we should be able to try every possible subsequence, because then that should fit, right? Because the constraint is values are really small, right? And so how do we do that? The other thing is that we can try all possible subsequences, but as soon as, let's say, maybe we had, I don't know, maybe we had 2, 3, 5, 4, 8, right? Once in your subsequence you have 5 and 4 in this order, right? 5 is bigger than 4. Then immediately you know you shouldn't include 4. If you have a subsequence that has 5, you shouldn't include 4, because then you don't have the non-decreasing property anymore. Okay? And so when we are doing a choice of a subsequence, if an element is smaller than the last one, so let's say our subsequence last one is, if it's bigger than the elements we are looking at, equal is allowed, but if it's bigger, then we shouldn't include this number. Immediately we know we shouldn't include this number, right? But okay, so that's the first observation, is that we can skip the number if it's smaller than the previous one. The second thing is that this can be done with backtracking, because what we can do is, for each number we have only 2 options. For each two options, either to take it, include it in our subsequences or not. And that's the principle of backtracking. So basically two choices here, either include or skip, right? And so for example, let's do a decision tree for this. So first we start out with either with 4 or without it. Okay, without it, it's just empty list. Okay, and then from 4 for the next element, we have two options, either include 6 or skip it, and so we'd have only 4. And then for 7 here, either include 7, and so 4, 6, 7, this is valid because it's non-decreasing, or skip it, right? And then here for this 4, either include 7 or skip it. So included is 7 for 7, and so you can see this is, we already did, with this we do the subsequence. We don't do just the subarrays. This is, otherwise skip it 4. And then again, we do the second 7. 7 is equal to the last one that we are looking at in our subsequence, so it's valid. And so we included 7, 7, or we skip it 4, 6, 7. And this is the last array here. This is the last array here because we reached the end. And so we stop when I is equal to n. Okay. Similarly for this 4, 7, for the last one, we either include it or skip it. So 4, 6, 7, or skip it 4, 6. Okay. But already you can see here that we have a duplicate here. Okay. And this is because of the equal. We have two values that are equal. So in our solution, we will need our results to be a set so that we can, so that adding duplicates value doesn't duplicate them, right? For that, in Python specifically, you will need to convert your list to a tuple so that set can check, can be able to check if with contains function. So you'll just need to convert your list to a tuple, but that's an implementation detail. Now let's just go back here to our other option is not picking 6. And so now if not picking 4. So if we go to 6, we have two options, either pick 6 or stay with an empty list. Right? And then we check 7. Is 7 smaller than 6? No, 7 is bigger. And so we are able to include it. And so we either include it or we don't. Okay? And you get the idea. Every time we just check, we already know that the rest of the subsequence maintains the order. The only thing we need to take care of is the new element and the last element of the sequence, if they are in order or not, right? Because we already maintained we know it's ordered, and we know the last value is the bigger value, right? And so for the new value x, we just need to make sure it's bigger than the last value, because if it's bigger than the last value, it's bigger than all the other elements, right? And so if it's bigger than the last value, it's safe to include it, right? But even if it's safe to include it, we still want to try all possible options, right? Because if we didn't try all possible options, then we won't have 4, 7, because 6 is bigger than 7 is bigger than 6, and so 4, 6, 7 is valid. But if we don't skip 6, then we won't have 4, 7, right? And that's a valid subsequence. Okay, so I hope that makes sense. And so with backtracking problems, it's really, really helpful to do a decision tree like this. This problem is very simple, so it's easy to think about it. But for complex problems, just try, if it occurs to you that backtracking may work, just try a decision tree. Yeah, so that's pretty much the idea. Now let's code it up and make sure it passes our test cases. Okay, so now let's implement this solution. So what do we need? So we need, of course, our helper function that will recurse and do the backtracking for us. It needs I, and it needs the subsequence that we have so far, right? And then of course we want to call it initially with 0 and with an empty subsequence, right? And then we want to have a set of the results that we want to return, and that's what we are going to return at the end, right? This problem accepts a set return value, I believe, but you could also just, if you want to convert it to a list, you could just do something like this. That should work. Okay, so now with this, we can now define our function here. We said that the base case is when we reach the end, we just return, but we also want to include this subsequence. But remember, we have a constraint that we need the length to be at least 2. We need at least 2 numbers. So we need to check that. So if the length is at least 2, which is bigger or equal to 2, then only in that case we want to add this list as a valid result. And why do we know it's a valid result? You will see here, we will make sure that we won't add an element unless it has the property of non-decreasing, right? And so here we have 2 options, either take it or skip it or leave it, right? Let's call it skip it actually. So for taking it, we have one condition, right? We need to maintain non-decreasing, and the way we maintain non-decreasing, which is increasing, is that we need to make sure that the last element of the subsequence, which is the bigger element in the subsequence so far, is actually smaller or equal to the number we are looking at. Because if it's not, then we won't maintain this property. So only in that case that we want to call it and add the number to the subsequence, right? But there is only one other case, is that what if it's the first element? If it's the first element, we want to include the number anyway, right? Because adding it won't violate the non-decreasing property because it's the only element, right? And so we need to say not subsequence, or you could also say length of subsequence equal to 0 if you want, or this, but in Python it's just more idiomatic to say not subsequence. And now for the skipping part, we don't need the return value because we just return, and we just use the subsequence, pass it in the parameter to save it here. And so, by the way, here, sorry, we need to go to the next slot because we just handled this number, we just added it. So here, similar thing, we want to skip the skip value at I. That's what we are skipping. Take value at I. And so here to skip it, we just not include it in our subsequence, and so we just call it on subsequence itself. And that should be pretty much it here. So let's reset. Let's run this. Yeah, we didn't define n. And the other thing also that is not here is that to add to a set, a list, you need to convert it to a tuple so that it's valid. And that should be it. Let's submit. And that passes our test cases. Yeah, so I think that's pretty much it for this problem. Please like and subscribe, and see you on the next one. Bye.